Here's a little video about one of the weirder kind of limit calculations that we as calc teachers ask you to do. It's a limit involving a root, and it's not a completely random limit at all. It actually is a difference quotient. If you're just studying limits, you might not have seen this yet, but it's actually the slope of the tangent line. This is what calculates the slope of the tangent line to y equals square root of x at x equals 9. Don't want to go into that precisely. I want to talk about the weird mechanism for actually evaluating this limit. And what you're told to do, and we'll go through the details, and we'll see there's a beautiful fairy tale associated with it, is rationalizing the numerator of a fraction. And that seems pretty weird, because usually in algebra you're told to rationalize the denominator. Okay, let me briefly sort of review how that works and in algebra and why you might do it. So let me just do a problem. Here's a very complicated looking number. 4 over the quantity 3 minus root 5 plus 1 over the quantity 2 minus root 5. We'd like to know if there's any simpler way to write that number. Maybe that's as simple as it gets. And in particular, is there a way to kind of combine those root 5s? Well, we know that when addition or subtraction happens in a denominator, it's really hard to deal with that. Okay, you definitely can't say this is 4/3 minus 4 over root 5 plus 1/2 minus 1 over root 5. That is absolutely not true. But there's this wonderful thing you can do. You can take each of those guys and you can multiply by what's called the conjugate. In this case, it's multiplied by 3 plus root 5 over itself. This is just multiplying by 1 in a fancy way. So that's totally legal. I'm not changing anything. I'm just simplifying. And now I'm going to multiply by the conjugate of this guy. You just change the minus to a plus. Why is that so cool? Okay. It's because this is a minus b, a plus b. So that's going to be a squared minus b squared. 3 squared minus root 5 squared. That's 9 minus 5. And that's just going to be 4. Oh, hey, it happens to cancel the 4. And then you still have the 3 plus root 5 on the top. So you might think, well, I've still got the root. But it's in a numerator, and it's going to be much, much, much better. Plus, okay, a squared minus b squared. 4 minus 5 is a minus 1 on the bottom. And then there's a 2 plus root 5 on the top. Let's see if I can squeeze this in here. So this is 4, and then they cancel. And so I've got 3 plus root 5. And then dividing by minus 1, well, that's the same thing as just turning that into a minus sign. Let's make sure it put parentheses there. So minus the quantity 2 plus root 5. Hey, this doesn't always happen, but in fact, the root 5s happen to cancel here, and it's actually 1. That's really cool. That it was seeming like this was a super complicated thing, and it was seeming like we could never kind of break the root 5s out of this prison they're in that doesn't allow them to interact algebraically. And yet we could break them out by flipping them up, rationalizing the denominator, and then they could interact and actually cancel. Okay, so something somewhat similar is happening with the limit story, but here it's that the root is in the numerator. Okay, now the real big difference here is that the square root is really not the problem here. Why is this limit hard to calculate? It's because the denominator is 0. If we just try to plug in, you should always think about, for a lot of cases, not the interesting cases, but for a lot of kind of boring cases, you can evaluate a limit just by plugging in. If it's a nice rational function or polynomial or root function or almost anything, in other words, any continuous function, and you're in the domain, you can plug in the value. That's what it means to be continuous. But this is one case where you can't. If you plug in h equals 0, that doesn't make any sense. Okay. So if you've done some problems like this already, which I hope you have if you're trying this one, what you've seen is that you want to get to a place where you can cancel something top and bottom, and basically to cancel out that h in the bottom. You do some sort of factor and cancel or simplify and cancel procedure. Well, there is an h on the top, okay? And so what we've got here is, here's the fairy tale, okay? We've got a knight in shining armor up here. That's this guy. There's our knight, okay? And he is ready to vanquish the evil knight. I don't have a picture of a specifically evil knight down here. Okay, but that's the evil knight. Imagine this guy's now turned evil. Blah. Okay, so this here's the good knight. This is the fairy tale part, in case you were wondering. Okay, he would like to vanquish the evil knight, but he's trapped in the castle, the evil castle of the square root. Okay, and if only we could break him out of the castle, then he could cancel down here. It's a little bit like what I was saying with sort of breaking out of the prison of the denominator before. But here it's the square root that's the prison, and I'd like him to cancel out the evil knight. Okay, so we know a way of moving around, of getting things out of square roots in creative ways. And so we multiply by the conjugate over itself. We have to do it over itself because otherwise we're changing the expression. This has to just be a fancy way of writing 1. Okay, but then that's the limit as h goes to 0. Okay, square root of 9 plus h times itself is 9 plus h. That's the a squared. Minus the b squared. Ooh, minus 9. Hey, that's nice. Okay, and then h. And this is where people usually stop and say, this was stupid. My algebra teacher told me never have a root in a denominator if you can help it. Why put one in there if it's not necessary? But this is where we have to pay attention to what's really going on in the fairy tale. Who was the evil guy? It was this h. The square root was not a problem. In the original expression, you could plug in h equals 0 there, and it's totally fine. We're not trying to do algebra with this or do anything complicated with the square root. We're just trying to plug in a number. And that's not hard to do with square roots. Okay, and it's not hard to do here with square roots. This part, we'll be able to plug in h equals 0 with no problem. It was this guy that had to die. And now that's going to happen because the h has been rescued from its prison. It now vanquishes the evil knight but dies in the process. It's very sad. It's one of those kind of sad fairy tales. And so now we've got a 1 on the top, and there's nothing going to 0 on the bottom. This guy, because of the plus sign, it doesn't go to 0. You can plug in h equals 0, no problem. Square root of 9 is 3. 1 over 3 plus 3 is 1/6, and that's the answer. And it turns out, if you connect that to tangent lines and stuff, turns out that's the slope of the square root function at x equals 9. A very, very important kind of calculation, and done thanks to the good knight and letting him escape the castle.